Okay, so picking up where we left off, right? So we wanted to balance, after the fluorines, I wanted to balance the nitrogens, because the hydrogens. Typically, when I balance things, if something's in the diatomic form, so N2 gas, for example, I typically leave that for the end, because that's typically one of the easier elements to balance. And so my next step after I balance the fluorines is to balance my hydrogens. Okay, so on the reactant side, I have 3. On the product side, I have 2. Okay, and so I have to do, you might remember this from really far back in math. I will get to the question after. You have to use the, I think it's least common, no, it's greatest common factor or something, least common factor. Basically, it's what's the smallest number that 2 and 3 go into? It would be 6. Okay, so in order to balance hydrogens, we're basically going to make sure that there are 6 on each side. And so to do that, we'd have to have a 2 in front of ammonia, and we would need to have a another 3 in front of HF. But we already had a 2 in front of it, which contributed 2 hydrogens, and so we'd need a total of 6 HF. Okay, this one is kind of one of the weirder ones to balance. But because, and so now we have 6 hydrogens on both sides of the equations, hydrogens balance, but because we changed the coefficient of HF, we now have 6 fluorines, but on the reactant side, we only have 2. So we almost unbalance the fluorines with that last step. And so what I'm going to do is I'm just going to see, okay, 6 fluorines for the product side, 2 for the reactant side. I'm going to have a coefficient of 3 in front of N2F2 to make sure that my fluorines are balanced. Okay? So we're on like kind of like the second to last time that I write the equation out. Up to that point, both hydrogen and fluorine are balanced. And so we just need to balance nitrogen. So on the reactant side, we have a total of 8 nitrogens. On the product side, we only have 2 in the form of diatomic nitrogen. And so we just need 4 of those diatomic nitrogens to balance. And the nice thing about balancing an equation is at the end, you can count up all the elements on each side and confirm that you did it correctly. And that's actually a strategy I used on the third problem I gave you, the one that starts with aluminum sulfate. Okay, that I did at the end to make sure everything was balanced. Okay, so for the number 3, the aluminum sulfate one, I first started with aluminum to balance. Right on the reactant side, I underlined it. I can see that I have 2 aluminums, while on the product side, I only had 1, which means on the product side, I need a coefficient of 2 in front of aluminum hydroxide. Okay? Now that I have 2 aluminum hydroxides, I have a total of 6 hydroxide molecules on my product side, while I only have 2 hydroxides from calcium hydroxide on my reactant side. And so I need a coefficient of 3 in front of calcium hydroxide to balance out hydroxide. Okay? And you might notice here that I'm kind of balancing groups, right? I'm balancing OH together here as a group rather than each element individually. Just because, at least in this case, I find that easier. Okay, the next step, now that we have 3 calcium hydroxides, would be to balance our calciums, right? So we have 3 calciums on the reactant side, but only 1 on the product side in the form of calcium sulfate, and so I need 3 calcium sulfate molecules for everything to balance, and that last line shows you my balanced equation, right? So my coefficients going from left to right would be 1, 3, 2, 3, and then below I have all my elements, and then you'll see a line between 2 numbers. On the left side of that line, that's how many I have on my reactant side. On the right side of the line, that's how many I have on the product side. If you don't feel comfortable balancing equations yet, I definitely recommend the strategy I did at the end of number 3, because if you see something's incorrect there, you can go back and try to fix it. But luckily for balancing equations, you always have kind of that way to check your answers. Okay. I know somebody asked a question. To get the total number of atoms, you multiply the subscript by the coefficient. Why not add them? So I'm trying to look at an example quickly. So I'm going to look at in the very last balanced equation for the second problem, 4N2, so 4 diatomic nitrogens, right? If you were to add the coefficient and the subscript, that would say that you have 6 nitrogens, but you have 4 molecules that each have 2 nitrogens, right? So 2 plus 2 plus 2 plus 2, so which is 8. Okay, so you do multiply them because it's saying you have 4 N2s, and in every single N2 compound you have 2 nitrogens. So you do have to multiply. Okay. And if anybody has any questions, feel free to keep asking. So stoichiometry, again, it's kind of hard to verbally describe it, but basically all it is, it's the mathematical process of converting between elements and compounds in a chemical equation. Okay, so I'm sure you guys are all pretty familiar with this, either from high school or at least this week. I'm sure you guys have had plenty of practice, but basically all it says is you're going to be converting between compounds in a chemical equation. And how do you do that? That's why our coefficients are going to be so important, because those are our molar ratios. And I'm going to show you that in an example right here. Okay, so this was actually, the equation was one of the ones that we just balanced, right? And as you can see, it is a balanced equation. It has all the coefficients. If you counted all the atoms on both sides, they should balance. And the question is, the above reaction takes place with excess dinitrogen difluoride. Okay, and we're going to go into what excess means in a bit. And it is found that 8.2 grams of fluorine is found in the resulting products. Okay, so fluorine shows up as HF, which is hydrogen fluoride. It's not an acid because it's not aqueous. It's in gas, so it's hydrogen fluoride. And so it's saying the fluoride component of hydrogen fluoride is 8.2 grams. Based on this, how many grams of ammonia were used in the reaction? Okay, and so there's kind of just a few things I want to point out here. So if it's 8.2 grams of fluorine, we should convert to moles of fluorine. So 19.00 grams is 1 mole of fluorine, and then 1 mole of fluorine is 1 mole of HF. Now there's a 1 with an arrow pointing to this conversion unit, and the reason for this is a time where our conversion unit is derived from a single compound, right? Fluorine is in HF, right? And so whenever you're converting moles of a component of a compound to the overall compound, your molar ratio is going to be dependent on subscripts, right? So in HF, the subscript of F is 1, which means there's 1 mole of fluorine per 1 mole of HF. Okay? So up to that point, if you cancel out all your units, we have moles of HF. We're not asked for moles of HF, we're asked for grams of ammonia. So here, we have to convert from moles of HF to ammonia. So 6 moles of HF is 2 moles of ammonia. Okay, and again, I drew an arrow to this, and because this is what we think of as a stoichiometric ratio, right? We're comparing a reactant and product to each other. When you're comparing 2 different compounds in a chemical equation, your molar ratio will be based on your coefficients in your balanced equation, right? So our coefficient for ammonia is 2 in our balanced equation, and our coefficient for HF is 6, which tells us that for every 6 moles of HF, there's going to be 2 moles of NH3. So that's how you come up with that conversion factor. And then 1 mole of ammonia is 17 grams, and it comes out to 2.45. Really, the whole point of this example was to show you, or to kind of talk about how you derive the molar ratios when it's 2 different compounds versus when it's a compound and an element within that compound. Okay, so if the elements within the compound, you use the subscripts as the ratio, subscript to the overall compound. If it's 2 different compounds in a chemical equation, you use the coefficients. Okay. Now going on to limiting reactants. This is a pretty big topic, again, for the rest of the semester. And so what is a limiting reactant? So when a reaction has multiple reactants, right, multiple things that combine to form products, one of them will limit the amount of product that can be formed, okay? And you'll be facing a limiting reactant problem, whether you know it or not, every time they give you the amounts of 2 or more reactants, okay? If they only tell you 5 grams for one reactant, it's not really a limiting reactant problem. But if you get grams or moles of multiple reactants, it's automatically a limiting reactant problem. Okay? And if it says the term excess, right, if a reactant is an excess, all it means is that it's not the limiting reactant. Okay, so if, and I'll get into my very simple explanation like that with the example. So the example, just kind of like a real life, really kind of easy to understand example of limiting reactant is if you have 1 jar of peanut butter, 1 jar of jelly, and 2 pieces of bread, how many PB&Js can you make? So obviously from a jar of peanut butter, you can probably make, I don't know, let's say 30 PB&Js, and from a jar of jelly, you can probably make 20 to 30 PB&Js. But if you only have 2 pieces of bread, that is your limiting reactant, right? That's preventing you from making anything more than just a single PB&J sandwich, okay? And so in this case, bread would be our limiting reactant in essence. Now, again, we said 1 jar of peanut butter can probably make about 30 sandwiches. So sometimes telling you that there's 1 jar of peanut butter is just an insignificant detail that does not matter. And so the same problem, but just worded differently, could be you have excess peanut butter and excess jelly along with 2 pieces of bread. How many PB&Js can you make? Okay, so it doesn't really matter how much extra peanut butter and jelly they are. You just know you're not going to be limited by those components by the term excess. Okay? And what's the typical limiting reactant question? This is almost always seen on the long answer portion as well as the multiple choice, but when it's the long answer question, you'll typically be asked, what is the limiting reactant? How much product can be formed? How much excess reactant there is. There's also often a percent yield portion. You'll see a very typical limiting reactant problem in the challenge problems tonight. Okay. We're going to go through 2 little questions. This one's just kind of me talking through a problem using not real compounds. The next one, I'll actually show you how to calculate the answer. Okay, so what is the limiting reactant would be the question, which we'll come back to. But if they ask you how much product C can be formed, right? We don't know what A, B, C, and D are. But let's say they want you to answer how much C you can form. So your steps for this, and they would give you how much of A and B you start with. Your process would be to convert the amount of A you have, right? So reactant A to how much C of product C that can form. And you're going to do the same thing for B. So I would personally convert, let's say 10 grams of A can form how many grams of C? And if I have 20 grams of B, how many grams of C can I form with that? The reactant that forms less product is the one that will be your limiting reactant, okay? Because it limits how much product you can make, okay? And that's why it's limiting reactant. You'll also almost always be asked how much excess reactant there is. So if B is the limiting reactant, they're going to ask how much, basically it's going to ask how much of A is left. But they wouldn't tell you it's A because that kind of gives away what is the limiting reactant. Okay? And so what you do here is you kind of work backwards. Okay? You take the amount of product C you can form, okay, and you convert that to the amount of reactant that is needed to form that stoichiometrically, okay? So if you can form 10 grams of C, you're going to stoichiometrically find how many grams of A it took to form C. And that represents the amount that you used up, okay? And so to find how much excess you have, you take your starting amount and subtract the amount that was used. It's kind of confusing in words, and I'm about to show you in numbers. I think it makes a lot more sense. So this is the problem we're going to do. You maybe will recognize, no, this equation is slightly different. It is not balanced. And you are told that if 32 grams of hydrocarbon, which hydrocarbon just means any compound with just carbon and hydrogen in it, so that's C5H12, reacts with a in a controlled chamber with 126.5 grams of oxygen, answer the following questions. So what is the limiting reactant? How much carbon, sorry for writing carbon twice, but how much carbon dioxide can be formed? How much excess reactant there is? And if you get 83 grams of water, what is the percent yield? Actually, yeah. And so what we're going to do from here, I did make a mistake at the end, so ignore part D. Sorry, while reading it I realized or just pretend it says 83 grams of CO2. Okay, so make a small change to this fourth question. It's 83 grams of CO2. I did that by mistake. Okay, so at the top, you'll show, I kind of just showed, I skipped the steps, but how I balance this chemical equation. Okay, so my coefficient for my hydrocarbon would be 1, my coefficient for oxygen would be 8, 5 for CO2, and 6 for water. Okay, and so my first step, they asked me in the second question, how much CO2 can I form? And so that to me tells me I want to convert my reactants to grams of CO2. So if I have 32 grams of hydrocarbon, I can find, using calculating my molar mass, that it's 72 grams per mole. And from our balanced chemical equation, we know 1 mole of hydrocarbon is 5 moles of CO2. H dot C dot just means hydrocarbon. I just abbreviated it. And then 1 mole of CO2 is 44.01 grams, which means we can form a little bit over 97 grams of CO2 from our 32 grams of hydrocarbon. Now we're going to do the same exact thing for oxygen. So 126.5 grams of oxygen, we multiply it by 1 over its molar mass, so 1 mole is 32 grams. We know from our balanced chemical equation that it takes 8 moles of oxygen to form 5 moles of carbon dioxide, and 1 mole of carbon dioxide weighs 44 or so grams, and based on the oxygen alone, we could form 108 grams of CO2. So in this case, our hydrocarbon is limiting because it prevents us from forming all 108 grams that oxygen would let us form, right? The hydrocarbon only allows us to form 97 grams. And so that answers your first two questions. The hydrocarbon is limiting, and we can only form the 97.6 grams because that is kind of the limit of capabilities based on the amount of hydrocarbon we started with. Okay. Now, part C asked us how much excess reactant do we have? So our hydrocarbon is our limiting reactant, which means we are going to have no excess hydrocarbon. It's all going to be used up to form this CO2 and water. Instead, it's going to be the oxygen that is in excess. And so this is the process I always use to find excess reactant. I'm going to take the total amount of product I can make, right? So we found that above. We found we could make 97.6 grams of CO2. I'm going to convert that to moles of CO2 by dividing it by 44, which is its molar mass. And then I'm going to convert 5 moles of CO2 as 8 moles of oxygen, right? We know that ratio from our balanced equation. And 1 mole of oxygen, remember it's diatomic oxygen, O2, is 32 grams. This gives us how much oxygen we used up, right? This stoichiometrically is telling us 113.5 grams was used in order to make that 97 grams of CO2. And so to find the excess amount of O2, you take the starting amount, 126.5 grams, you subtract the amount of oxygen that you used to form the products, and that gets you your excess, which in this case is 13.0 grams. Okay? And just the percent yield part is at the very bottom. Again, I apologize. I wrote 83 grams of water. Just pretend it said CO2. And so again, remember percent yield equation is our and actually we go over in a second, but it's experimental over hypothetical times 100. So experimental is how much you actually collected, which we were told in the problem was 83 grams, not percent. And we should have, hypothetically, if the reaction was perfect, we should have gotten 97 grams. Okay, and so we do experimental over hypothetical, multiply it by 100 to get it in terms of a percentage, and we find we got 85% as our yield. Okay, and again, percent yield, that is talked about on this slide. So the equation is listed. It's experimental over hypothetical, theoretical. Hypothetical can also be used instead of theoretical. But just note that, so your experimental, they have to tell you what your experimental amount is, or you're going to calculate it, because that is how much you get in real life, okay? Your theoretical amount will be based on math, your dimensional analysis, right? How much should you have gotten if everything worked out perfectly, right? And so I kind of relate this to, and I know this semester is a little different, but when you're in lab, right? Sometimes you'll be doing a reaction and you'll get 10 grams, which is your experimental, but you theoretically should have gotten 20 grams, how much you should have gotten based on the amount of reactant you had. Okay. So right now, if you don't mind just signing in, as well as the activity. So tonight's activity is just out of the chapter 3 topics, please just put what you feel least comfortable with. So what gives you the most difficulty from these topics listed? Again, these topics are going to be the ones that we focused most on the Monday session and next Wednesday's session. We'll spend more attention on these problems. How do you sign in? So to sign in, you just put your net ID. It should be 3 letters followed by 5 numbers. And the letters are most likely your initials. It's what you log into Husky CT with. So mine, for example, is RPK 15103. Okay, I'm just going to go. You can continue to do that. I'm just going to talk about Monday's activity, because if you don't mind, I don't want to give you guys homework, but if you don't mind doing this for Monday, there is still challenge problems and stuff, so don't go quite yet. But Monday, if you could create or find a problem, right? So if it's a super difficult homework question that you've been stumped on, feel free to bring that in. So find one that did challenge you or continues to challenge you, and bring it to next SI, right? The activity for Monday will be for you guys to submit these problems to me, whether you make it up on the spot or not, from chapters 1 through 3, any of the topics I've listed, and those will be used to make review problems for Wednesday night. And if there are errors or things that I need to fix, I will do that, but it is helpful. I also suggest, if you can, create one on your own. Please try that, because sometimes actually creating these problems can help you understand the material a lot better. And so if you can create one on your own, that's also awesome. Also, if anybody's watching this recording through the link and not live, feel free to email me one of these, your problem that you made. I will definitely include it or look at it to make the review. Yes, I can go through the question with the protons in just a minute. I'm just going to show the challenge problems, and then I'm happy to go over the proton question as well as anything else people want to go over. Okay, so these are the 2 multiple choice questions I made for tonight's challenge problems. I kind of scrambled to get number 2 together. So one thing I'd like to note, all the numbers in front of MN should be superscripts, right? They should be kind of small numbers up. I didn't mean to leave them like that. So 53 should have been a superscript before a manganese. But this is kind of number 2 is a multiple choice version of an isotope question. It's pretty rare to see it in terms of a multiple choice question just because it's very difficult to make into multiple choice, but here's kind of an example of one that could be. So it's not your most traditional question, but it was my attempt. I'm going to go to the next slide in about 10 seconds if you want to take a picture, or I can come back to it in a bit. Ready? Okay. You will notice that number 4, that is actually a chemical equation we balanced already, but it is a really nice percent yield question. I actually really like it. And number 3, I would probably star. That was one that, again, traditionally shows up on exams. Typically, again, a long answer portion of the exam, but again, a really good question, and it comes up year after year where you are solving for the identity of a metal. So the unknown metal is X. Okay, and it is a good and tricky one. Okay, about 5 more seconds if you need a picture. And again, you can always access these videos online if you want to just come back to them. Okay. And number 5 is a stoichiometry problem, and number 6 is your classic limiting reactant problem. But again, number 6 is the one where they ask you to write a balanced chemical equation. And that portion was very similar. I actually had to do one like that on my exam as well. And they do give you enough to write the states of matter for all of those. Okay. Are there any questions remaining? This was the last slide. If not, somebody asked me to go over the vanadium 2+ question. I'm happy to do that. But if there are any questions kind of regarding tonight's things before I wrap back